All right, we need to talk about magnetism. Hopefully you have your magnetism notes out in front of you. Magnetism will be the third non-contact force that we've talked about in physics this year. Non-contact forces are interesting because, as the name implies, two objects do not have to be in contact to exert that kind of force on each other. Magnetism is one of those. Objects don't have to be in contact to exert a magnetic force. There doesn't even have to be any matter between them for that to happen. So it's an interesting concept, and it's one that is very hard to explain. We'll give an explanation today, but you may find that it's not very satisfactory. So let's talk about magnetism. The first thing you need to know about magnetism, which you probably already do, is that magnets have polarity. There's a north pole and there's a south pole. And I think the question that's begged at this point is the fact that why do we use the term north and south? Those are clearly geographic terms. And magnets seemingly don't have much to do with geography, but there is a connection, and the connection is that the Earth itself is a giant magnet with a north pole and a south pole. And so that's the reason why we use geographic terms to describe magnets, is because the biggest magnet that we know of is actually in the Earth itself. And we'll talk about that more in a minute. Just as far as properties of magnet, another property is if you cut a magnet in half, what do you get? Well, hopefully you know this. You get two north-south magnets, two magnets that have both a north pole and a south pole. You cannot make a monopole. These magnets can sort of quote-unquote asexually reproduce, and you make two smaller magnets of half the strength, and you can cut each of these into two smaller magnets, and again and again and again. Because it doesn't have anything to do with the location of the S and the N, it's the orientation of the molecules within this magnet that really matters. Number 3 is the next thing on your notes, and you probably already know what goes there. Like poles blank, unlike poles blank. Well, like poles repel and opposites attract, and you probably knew that since you were about 3 or 4 years old. My son came to me when he was 4 years old and said, "Look, Daddy, north and north doesn't work, but north and south works." We understand this, we get this, and it's very similar to the concept we learned with electrostatics with positive and negative charges, but it's not exactly the same thing. We'll learn about that a little bit later. When we talk about repulsion and attraction, north and north repel, north and south attract, this is when we need to start talking about a compass. A compass is really a very simple device. All it really is a suspended magnet. It's a suspended magnet that seeks geographic south. So let's look at a compass real quick. I have here a compass, and as you can see, there is a very small magnet inside this compass that is suspended. I know it's a magnet because it'll respond to other magnetic fields, as you can see here. So the way to use a compass is you simply let the needle come to rest. This needle is responding to the Earth's magnetic field, and then if you align the north side of your compass with the painted end of that magnet, usually it's painted white or red, that gives you the northerly direction, and therefore you could read your other cardinal directions off of that. So this is a magnet. As we know, north end of magnets seeks the south end of others and vice versa. So let's just look at this compass and let's test and see what end it is. First thing I'm going to do is simply mark on here which direction is north. You can see by this magnet that it's telling me that north is this direction. So theoretically, I can put a magnet right here beside this one to mimic Earth's magnetic field. I can use this magnet to mimic Earth's magnetic field, and theoretically, the compass is not going to move. And let's do that real quick, and let's see what we get. So there's my magnet. I put it right beside the compass and oriented it north and south, as you can see here, but strange thing happened. If you notice, the magnet flipped. It's oriented in exactly the same direction that the magnet tells me, but when I put the other magnet up to it, it flips. If I reverse the polarity of my black magnet, the compass actually stays in the same direction. So now we have a couple of questions to ask. We know this is a magnet, and we know this is a magnet. North end of one magnet seeks the south end of the other. Well, that means that the red end of my compass is the north end of that small magnet, because it seeks the south end of my magnet. Not only does it seek the south end of this magnet, it seeks the south end of any other magnet, including Earth's magnetic field, which is what it's doing right now. So if this is north and it seeks magnetic south, that tells me that this magnet is actually incorrect. I know that this is geographic north, that's true, but let's understand that we're not measuring real geography when we're using a compass. When we're using a compass, we're looking at the Earth's magnetic field, which doesn't necessarily coincide with the Earth's geographic poles. So actually, what this magnet is telling me is that the north and south poles are switched. In other words, compasses point north because the magnetic pole in the northern hemisphere is actually the south magnetic pole, not the north magnetic pole, and vice versa. So if you look at this globe, geographic north pole, we understand that, but that's actually the magnetic south pole, and vice versa, geographic south is magnetic north. So this is an interesting concept. If you take a look at this picture I'm showing you here, the point is that the geographic or the magnetic poles can and have reversed a number of times in Earth's history. And there's a long discussion that we can go through with this and how it's all happened. But just know this, that today, this is the way Earth's magnetic poles look, that the magnetic south pole is actually where the north pole is and vice versa. But there have been times in the past, numerous times, when the magnetic poles have flipped and north has been in the north and south has been in the south. And actually scientists think that we may be undergoing another magnetic reversal now. So the magnetic poles are not constant. Neither are they the same thing as the geographic poles. If you look at this picture, notice the axis of rotation of the Earth comes through here with this black dotted line. The axis of the magnetic poles, however, are not necessarily the same. In fact, they're hardly ever the same. You can see in this photo on the left, or the picture on the left, that the magnetic poles have wandered through the years to the point that if you use your compass and you begin walking north in a certain place, for instance, if this is where the pole is now, you'll reach this point, and then when you pass it, your compass will tell you that north is actually back the other way, when in fact north is still in front of you because you have not reached the geographic north pole. So the point is that the magnetic poles reverse, they wander, and the reason is because the magnetic poles are due to this molten iron core that is inside the Earth. It's liquid and it moves and it changes. Therefore the magnetic poles can change as well. All right, let's look back at the notes. There are a few materials that are permanently magnetizable, notably iron, gadolinium, cobalt, and nickel. Really, of those four, iron, cobalt, and nickel are the main ones that are typically used in the magnets that we know of. These materials are said to be ferromagnetic. They have properties, specifically with their outer electrons, that make them permanently magnetizable. And we'll talk about in a minute, technically, all materials have properties that can be made to be magnetic, at least temporarily, but not in a permanent sense like these can. So look at number 6 and 7, and I would put a star by those if I were you, because this may be the most important part of the notes. Where does magnetism actually come from? What is it all about? Well, this guy named Ørsted discovered that if you move an electric charge, all you have to do is take an electrically charged object and move it. That creates a magnetic field. In other words, magnetic fields are all about moving electric charges. It's as simple as it sounds. All you have to do is take an electric charge and move it, and you've created a temporary magnet. Now, it's interesting when we get down to the atomic level, because the smallest electric charge that we know of is an electron. And electrons are, in fact, moving all the time. So technically, all atoms have the building blocks of what it takes to be magnetic, but the problem is there are these things called domains. These electrons are spinning around the atoms in certain domains, and if you look at this diagram here of, let's say, a nail that is not magnetized, the domains in most materials are simply not aligned. That means that the electrons are not all spinning in the same direction. Therefore, their magnetic fields sort of fight each other. You might picture it that way. And so there's not one overall magnetic field that we can get off of this nail. It's not said to be a magnet as we know magnets. But if we align those magnetic domains to where all the electrons are spinning in the same direction, then that material is said to be magnetic. And it looks, so it doesn't look like this, but we can picture it as this nail here, where all the domains are now aligned in the same direction. And there's a number of ways to do that. The best way to do it, the most common way, is to apply a current through a magnet, magnetizable material, or to simply expose it to a very strong magnetic field of another magnet, and that will align all the domains to itself. This is often done in context of heating a material to a certain temperature so that the molecules, the domains, are easier to move. So it's all about moving electric charges, and if those electric charges, those domains, are moving in the same direction, then we can get a material that is a magnet, that the domains work together, and we have one single magnetic field that we can measure from that object. And it follows that if we simply align the domains to make a material magnetic, then all we have to do is simply randomize them or unalign the domains to destroy the magnetic properties of a material. And you can do that by dropping a magnet. That causes a lot of vibrations to go through the material. That can unalign the domains. You can heat it up. You can expose it to another magnetic field, and that can happen if you had the old VHS and cassette tapes. Those tapes actually work by aligning magnetic material on the tape, and if you have an old one, you might notice that it doesn't work as well. And the reason is because probably throughout the lifetime of a VHS or cassette tape, they get exposed to stronger magnetic fields that simply realign the magnetic material in the tape. Number 11 on your notes talks about magnetic field lines. Magnetic field lines are similar to electric field lines. There's a magnetic field surrounding every magnet, every magnetic object, and that magnetic field line is drawn as a loop or as a number of loops that point from the north pole of the magnet to the south pole of the magnet. So it looks something like this. In your notes you have two pictures of magnets that look really similar to this one. Just pause the video and take a minute to draw the magnetic fields around those two magnets, and they'll look just very similar to what you have here. Alright, hopefully you've done that. And now that you know what the magnetic field lines do around a magnet, let's ask ourselves, how do we draw the magnetic field lines for the Earth itself? Well, we talked about the fact that the Earth's magnetic field right now is actually reversed in comparison to the geometric or geographic field, or the poles. And so the field lines for the Earth actually would be drawn, we've already looked at it, something like this, where the field lines go from the North Pole to the South Pole. So the field lines for the Earth look like this. Alright, let's go ahead and move on with the notes. At this point, you have 12, 13, and 14 at the bottom of the notes. You can go ahead and cross those out. Those are about solenoids, which are very interesting, but we're just not going to talk about them in this class, as well as number 15 on the back. So if you'll go